Thank you. Especially thank you for coming today after the long break. It's also been a long break for me. This pretty picture in the background is unfortunately not my Infinite Serpent, but I thought it would be good to start with that one. This works belongs to the statutory topic number 7. By the way, I think that statutory topic is a common mistranslation of the term temat statutowy, but it's very common on the internet, so I'm going to continue this tradition, although it is incorrect as far as I know. So temat statutowy number 7, the geometry of maximally non-integrable distributions on manifolds. So this is done by the group of Paweł Nurowski, which consists of him and me, I guess. What is the objective of this topic? In its greatest generality is to study pairs of a manifold and a subbundle of the tangent bundle, so something we call a distribution, such that if we keep taking sections of this subbundle and the iterated Lie brackets, what we get this way will eventually span the entire tangent bundle. So this is the sort of distributions that we want to study, and that's a very general goal. So typically, if you see some task that
is it related to physics in any way?
It could be. There will be a relation in a moment, although we approach it mathematically. Yes. So I will talk. There will be one slide about applications and inspirations. Anyway, so in mathematics, typically, if you see the phrase "to study something," classically you understand the following under that. The goal is to classify those things up to some notion of equivalence. I mean, typically there are way too many objects to talk about every single one. We want to divide them into equivalence classes. And the classical tool to do this is invariance. So you want to find quantities that depend only on the equivalence class. So in this case,
excuse me, shouldn't that parameters little letter r also be included somewhere? Because clearly there is a certain finite number of those plus and brackets, so something depends on this.
yes, for all integers r. So all iterated Lie brackets were, I should add r is an integer. Positive integer.
I understand, but if r is equal 1.
Yes. No, so we take all iterated Lie brackets for all possible positive integer values of r.
As far as I know, it's also the integer, isn't it?
Yes, it is.
Okay.
But I say we take all of them.
R is not integer, it's something larger than 1. No, it's anything.
We take all sections which can be written in this form for all possible values of r. Okay?
R is running. 1, 2,
Yes.
4, 5.
So D depends on R.
No, d is fixed. This is a condition on d.
D.
For every given d, if we take the set of all sections which can be written in this.
Such a subbundle.
Yes.
Which clearly depends on the number R.
No.
We take all of them. 1, 2, 3, 4.
We
5.
introduce a condition on d, and the condition is the following. If we look at the set of all vector fields which can be written in this form for all possible values of r, then we want this to span the entire tangent bundle. Then, by the way, we call such a distribution bracket generating, or maximally non-holonomic. Okay?
Maybe
This will become
easier
clearer soon.
Draw something which is maximally holonomic and then to say what is.
Yes. Well, I think this will appear on the next slides to some degree, but of course the maximally holonomic is just an integrable distribution where, I wanted to say it later, but just to set this thing clear, what is special about those distributions, there is this celebrated theorem of Chow and Rashevsky, which tells you that this condition means that you can get from any one point of M to any other point of M along a curve which is always tangent to this distribution. So even though this distribution could have very small rank, you are able to connect any 2 points by a curve always tangent to this distribution. And for instance, from the point of view of control theory, this means that if you have a system with a lot of degrees of freedom, but you're only able to directly control just a few, and well, this few is given exactly by fixing some linear subspace in each tangent space so that you get a distribution. This condition means that you can control the system from any configuration to any final configuration, just applying your... Ale o łyżwiarzu to ja mówiłem 2 lata temu. I nie chcę jeszcze... Tu się pojawi też łyżwiarz. Okay. So anyway, the ultimate solution of this would be to find enough invariance so that we can find and describe all equivalence classes, and this is totally hopeless, so that's not what we do. And this talk is about a much more modest idea. But anyway, this is how invariants arise, and we are going to talk about some very basic invariants. And those most basic invariants of distributions are the following 3, the so-called growth vector, the symbol, and the symmetries, the algebra of symmetries. And I'm mostly going to talk about the growth vector, but the other 2 are also going to appear. Okay, so much for the background. I already spent too much time on that. So here's the interpretation and inspiration, and this is where we touch physics, and perhaps the only point of tangency with physics. So usually we interpret such a system as such a mathematical object as a non-holonomic system in some sense. So the manifold M is viewed as a configuration space. The distribution D gives us some constraints on the possible trajectories of the system in its configuration space. So, well, for example, if you define some Lagrangian on the tangent bundle to M, you can view this as some non-holonomic mechanical system, and you can ask about its evolution. If you add a metric, I mean an inner product.
Why is this non-holonomic?
Well, non-holonomic this is an assumption. So actually, it's maximally non-holonomic, which means
This is an arrow which indicates that if I define the Lagrangian, then it follows this is non-holonomic. I know a couple of Lagrangian non-holonomic systems.
there's a very informal arrow, but there is a D. The data of D, of the distribution D, introduces constraints, which are to be non-holonomic, which are to be non-integrable.
Red may lead to
May be interpreted.
an arrow in a weak cell. Yes.
Yes, I should use a squiggly arrow, but I couldn't recall how to do it in later. Squiggly arrows are good for informal arrows. That's exactly what I was looking for, but I couldn't recall how to do it. But the one that is closer to me is the second one. If you add a metric, by which I mean an inner product, a positive definite inner product in each fiber of this distribution, you can interpret such an object as a problem in optimal control theory. So you can get from any point to any other point along a trajectory that is tangent to the distribution, but now that you have an inner product on this distribution, you can measure the length of such a trajectory, and you want to minimize it. And this is a highly non-trivial problem. Still, there are very many open questions about that.
Speaking about connections with physics, there are various good physical theories that have constraints.
Yes, sure.
This is applicable to such systems. Dirac brackets and all this.
Yes.
Theory.
By all means, yes. But this is just the very basic geometric structure on it. So it's just
Sure,
the.
Do your results in any way
No. Well,
throw some light on systems which have these constraints?
I do not know this. I would be happy if someone said this. I would be happy if someone noticed such a thing.
Even simple electrodynamics had a constraint in the form
Yes,
of a
sure.
Gauss.
Yes.
But they are holonomic.
Yeah.
Electrodynamics, they are holonomic.
Yes. So let me proceed, because this is just the very, very, very beginning. So I don't want to get stuck at this stage.
But
Yes.
car with
Yes, exactly. A car. Exactly a car.
many wheels. Is
So,
clearly not-
2 years ago.
not in the
Yes.
fashion of
So 2 years ago, I spoke about the ice skater and about the monocycle and all that. There is a car. There is a famous example of trailers at an airport where you keep pulling this chain of trailers with luggage. So there's one very well-studied example, and this snake is going to be quite similar, but actually, I think more interesting. So anyway, here's the program of our absent friend Paweł Nurowski to obtain mathematically interesting examples of maximally non-holonomic distributions as configuration spaces of non-holonomic mechanical systems. So this is not to say something about those systems, well, at least not in the first place, rather than to produce interesting examples from a mathematical viewpoint, from just saying that we connect some pieces together, we add some wheels, and we study the constraints that this has.
So the carriage with the four
Yes,
wheels.
exactly.
Where the front wheels are moving.
Yes, absolutely. Yes. This
Has
is
that been studied?
yeah, a lot. Yes, that's one of the basic examples.
So what is this mathematically interesting example?
Well,
For the configuration space for the simple carriage with the two wheels movable, which is different from what we know from the book. I don't know whether the problem is in
about two wheels movable, you mean that they can turn, right?
Yeah. I mean,
Yeah. So this is an example of a system that, for example, has, as far as I remember, growth vector 2, 3, 4, I guess. So it produces an example of some, produces an example of a member of some particular class, equivalence class, of distributions, and it can be described in a few words, which is nice. So that's the point, actually, to be able to describe something in a few words rather than writing formulae. So Paweł Nurowski proposed to study some things he called geometric robots. So a geometric robot is a planar mechanical system built from segments, joints, and wheels, and those wheels roll without skidding on some flat surface. And I will show examples in a moment. That's just a definition. You don't need to learn it by heart. But basically, up to, say, the lengths of the segments and positions of the wheels, this is a pretty combinatorial structure. That's basically just some graph with some decorations, as you will see on the next slide. So those are some examples of...
In practice, it is exactly the position of the wheel which counts.
So, depending on...
the car, this is somewhat...
Depending on what kind of invariance you want to consider,
For me, the position of my wheels is rather important.
I would say that there are generic positions and special positions. So generic positions are all qualitatively the same.
The generic means that my car is somewhere.
Well, no. I mean positions of the wheels on. No. I mean positions of the wheels on this particular robot. So if your wheels were
attached to the car, so they...
exactly, but the question is where they are attached. In a car, well, not an expert on cars, but I don't think this matters a lot. But for example, for snakes and trailers, it does matter. So there is a difference between, say, a chain of segments where the wheels are put in the middle, like the one you see on the left, and when this, say, this middle wheel, if it were at the end point of the middle segment, that would make a big difference. So in this sense, the positions matter. But so those are some examples. So you should view these as some rigid segments. They are connected by joints that can rotate, and those little symbols are wheels. So those wheels are attached to the segments. They have to roll on the surface without skidding.
So should I understand that the thing in the middle cannot move?
It can.
It can?
Actually, it can.
Yeah,
It is quite interesting that it can. It is non-trivial that it can.
The question
It's a very nice one.
those wheels roll.
Pardon?
I mean, they can roll parallel to the line.
Exactly. So there is a pair of wheels. They are not allowed to skid. Just like any reasonable...
Skidding is a different thing. A parallel wheels can only skid. Also skid. The skidding means what is happening, at least in the physics, what is happening between wheels and the undergoing surface.
Yes, exactly. That's the point.
And
Yes.
I'm asking whether this wheel...
They are rigidly attached to the... They are attached to some axle. Yes.
Parallel to the...
Yes. Absolutely.
That's the
Yes.
question.
Absolutely. Yes. Yes. So, in other words, the simplest interpretation is the correct one. Always in this talk. So the question we ask is which invariance of the distribution that you can define on the configuration space, which invariance...
Just to answer Professor Zalewski, this middle device is one of these crazy things on which you drive by moving left and right, left and right. You can see them in the park. It's a huge structure.
In some sense,
which has 3 wheels,
Uh-huh,
right?
uh-huh.
And when you step on the
Yes,
left and right,
that's-
you can
in
go
some
up.
sense this is
Structure of the wheels is
roughly that.
Yeah.
Yeah. So the question is, which invariance of the constraint distributions could be, I wrote determined, but what I mean is explicitly deduced just from the combinatorics of such a graph. So say that I see that the last one, right, is some cycle of length 6, it has wheels exactly at every second segment, otherwise, by the way, it wouldn't be able to move in any reasonable way, except for turning. And what I ask is, can I find some magic formula that just from this data will tell me that the, say, the growth vector, which I am about to define, so far believe me that there is such a thing, that it is such and such. So are there some things that we can say about the constraint distribution just by looking at the picture? That's the question. Well, so yes, so what would be the candidates for such invariance? And the simplest candidate is the growth vector. Honestly, the simplest thing you can say about a distribution is its rank, but the rank is very easy to determine, so let's not talk about the rank, let's talk about something slightly more complex. So the growth vector can be associated.
The define, so what is the rank? Because I don't know.
The rank is the dimension of the fiber of such a distribution at a given point. We assume that this distribution is of constant rank. Okay, so the growth vector is a similar invariant because it also depends on a point, so we define it point-wise. So we assume that we are given a distribution D and some point M, and now we are going to do the following construction. So bear with me for a moment. So for each integer I, we do it for each integer I will take all vector fields which I can obtain by taking at most I sections of the distribution and computing an iterated Lie bracket. So I look at all such vector fields, then I take the values at the point M, this gives me some vector subspace of the tangent space at M, and I call this subspace D superscript I of M. Okay, well that's a natural construction, produces something at a point. So a mathematician would say that it produces a flag of subspaces in the tangent space at M. The more vector fields you take, the bigger the subspace you get. Well, it cannot be bigger than the tangent space itself, so clearly this process is bounded. So let Di be the dimension of the ith subspace that we obtain this way. So if you think about it for a moment, you see the following facts. The D1 is just the rank of the distribution. Then those numbers D have to grow strictly until at some point they stabilize. And once two subsequent ones coincide, they just keep being the same. You can think about why this is true. I don't want to waste time on that. So
Not stay equal for the
no, actually not. It leads to some interesting things to try to see why this is so, but I don't want to spend time on that. All right, so this finite sequence of integers, starting with the rank of the distribution and ending with this maximal dimension of a space that we can generate this way, this sequence is called the growth vector of the distribution at a point. Okay, so that's a very simple invariant. It is intrinsically defined. It does not depend on any coordinates. It's just a string of integers. It depends on a point, right?
So is there an upper limit for this?
Yes.
DR?
Well, the upper limit is the dimension of the manifold. So, in particular, if this ultimate D is equal to the dimension of the manifold, we have this thing that I call the bracket generating distribution. So we are interested in those things. Otherwise, you could take the biggest thing you can generate, and that gives you sort of an integrable envelope of your distribution.
In this case, is it interesting how fast it grows? So how
Exactly.
steps?
Well, also. So we'll get to that point. We'll get to that point.
How fast?
Okay, whether you need only one step?
Yeah, exactly.
Or
So,
three or-
yeah. So, I mean, for example, from the point of view of control theory, typically the faster the growth is, the better, because
It means D1 is equal to capital D.
well, that would
D2.
yeah. Well, yes, yeah, exactly, yes.
So a short.
That would be a very fast growing flag, and that would be very controllable, very easy to control. But I don't want to get into that at the moment. Now let me just say that if your data is analytic and if your manifold is connected, then this growth vector is constant on some dense open subset. So there is some big dense open subset of what we will call generic configurations where those integers do not depend on the point. And we can just restrict to this subset of generic configurations. So generically, this is just given. There are some special points, some lower dimensional strata where this thing can become degenerate, where it's harder to control our system. I don't want to get into that. So those are some singularities of the distribution. A very interesting thing, but we don't go there.
Some robots are stuck in the corner.
Exactly. Yeah. And actually, those are also invariants of distributions. So those are important, but don't want to go there. Okay. So back to geometric robots, the question is, can we find some combinatorial formula for the growth vector of a geometric robot at a generic configuration? So we've got some graphs, some sticks, some wheels. We just look at how it looks like. We take a generic configuration, and can we just guess the growth vector from looking at this robot? And at first I thought, well, maybe yes, that would be a nice project to do. A growth vector is such a simple thing. So how would we go about this? My idea was that maybe we could do it inductively. So you could imagine that you build your robot by subsequently attaching edges. So you start with just one point, you attach an edge, and so on and so on. So maybe if you know the growth vector of a smaller robot, you attach an edge somewhere, you can deduce what will be the growth vector of the new one. That sounds not totally crazy. So how would you test such an idea? Well, the easiest thing to do is just to produce a chain of segments. So those chains of segments are what we call snakes. So an n-segment snake consists of a chain of n rigid segments of unit length. Then they are connected by freely rotating joints, although everything is planar, so just rotating in the plane. And each of them is equipped with a wheel. For convenience, I put the wheel in the middle of each segment to make it as simple as possible. Of course, you could say, well, maybe I don't need to put wheels on some of these segments. So to obtain the simplest case, we put wheels everywhere. And the condition is, as we have already remarked, that the wheels roll on a planar surface without skidding. So this is an n-segment snake. This defines this robot.
There's just one.
Yes, exactly.
And then there are no wheels.
Yes, exactly. Then it would be just have this tail that could do whatever it wants. Exactly. So those are the snake. A one-segment snake is just the ice skater.
Is it important that there is just one pair of wheels per bond? That's the point.
Yes, absolutely. Yes, otherwise, if you had two, then the segment could only move along a fixed straight line. So that would be an integrable constraint, actually. And this way your system would drop to a lower dimensional manifold, could still play with that.
So that does not apply to the trains?
Yes, exactly. Yes, that's a good point. That is a good point. Although, well, somehow no, trains are able to trains are able to go along curves.
If I have flexible train.
Yes. Yes. Well, okay. So anyway, this defines this family of robots called snakes, which are parametrized by the length, the number of segments, I mean, n. So can we guess the growth vector for the snakes? Well, I thought I could. So, before I do this, let me just say how does the configuration space look like? So for the n-segment snake, I'm going to designate one endpoint of the snake as the head. This is important both for the snake and for doing what we want to do. So always one endpoint is the head of the snake. So I write the configuration space as a Cartesian product. There is an R2, a plane that parameterizes the position of the head. And there is an n-dimensional torus, which parameterizes the orientations of the segments, whichever way you like. You can do it in many ways, but it's always a torus.
Why is it torus? Why is it not just from 0 to 2 pi?
Well, yeah, but if it goes, I mean, I assume that those snakes can self-intersect and do all sorts of forbidden things. Really, everything will be totally local in what we do, so we don't really have to think too much about this thing being a torus. So now, well, the dimension of the configuration space is the number of segments plus 2, as we can see from that. And now we have this constraint distribution. So the first question we ask, what is the rank of that? So the rank is actually easy to determine, and that's a very nice exercise you could give to school kids. So you have one segment, and you want to ask, how can this thing move? So you imagine you drag one endpoint. Can I find the pointer? I cannot find the pointer, so I'm not going to point at it. Okay, but I'm connected to this thing, so try not to kill myself. Okay, so let's look at one of the endpoints, maybe this one. So imagine that you drag it with some velocity given by this vector. So, well, in order for this thing to stay undeformed, the parallel component of this velocity vector has to stay constant along the segment. And then what you know about the normal component of this velocity, well, it has to change linearly. And now you have the constraint that tells you that the normal component has to be 0 at the middle, and that already tells you that what you get at the endpoint is just a reflection of the velocity at the other endpoint along this line. So that's a very nice problem to give to school kids. You don't really need to compute anything, and you can see how it has to move. So okay, so if we know the velocity with which we pull one endpoint, we compute the velocity of the other endpoint by a reflection. So this way you can, of course, figure out how a full snake will move, right? For every segment you just reflect, reflect, and reflect. So what does it tell us? Well, it tells us precisely that the head of the snake can be dragged freely. You can drag the head along whatever curve you like, and then the tail will follow in some uniquely specified way. So just by looking at those pictures, we know this.
Can the snake progress this way or only wiggle?
So this is a very good question, because of course if we just pull the snake, we can do with it whatever we want. There are no singular configurations. But the snake doesn't do it this way, of course. The snake controls the angles between the segments by contracting some muscles. And then it could be in a singular configuration, actually. So I don't think that it has configurations from which it cannot exit, but it has configurations which are harder to exit. And we can talk about it later. But so this is a snake that is explicitly dragged by its head.
There is a kind of a toy for kids, which is a real snake.
Yes.
Which is segmented, and when you hold it,
Yes,
it
I remember this. I loved this toy. I remember it.
And
Yes.
so that is.
So if it were doing that on a surface, it should.
It never progresses because you hold it. But
Well,
it
yes,
wiggles
yes,
in a
yes.
crazy way.
So I had a talk about such a 3-segment snake. I didn't give it at the seminar, but I gave it at the Festival Nauki and at some other places, which was exactly about how such a 3-segment snake can move only using some muscles that control those 2 angles between the segments. And this is a lot of fun. But not this time. So, oh yeah, so I'm supposed to show you how this works. So here I have such an infinite snake. I'm dragging it by its head. Those blue lines show you the orientation of the segments. Those red lines show you the positions of the curves. So you can observe that the red dot always moves tangent to the blue line. And whatever I do with it, it will do something. It's quite interesting because it remembers what happened to it. So if you imagine that this thing, now anticipating what I'm going to do later, this could be infinite.
This segment,
Well, in this model, yes.
This model, yes, realization.
Yes.
but that seems to contradict the construction.
No.
They can cross.
The construction is totally local, so. Also, I mean, snakes do it a lot, right? They coil and.
Yeah, but they never penetrate.
Because they are not to do
Yeah,
because they are in 3D.
They are not common.
So
Okay.
it's even worse in 2D.
Well, yes, exactly. That's what you're saying. Yes. So this is an idealized snake. Yes. Yes.
What actually happens? How do you integrate that in the middle of this? When this one of the segment crosses, there must be. Is there any?
Nothing happens. Yeah.
The segments do not see it.
Do not see each other.
You can believe that the snake lives on some multiple sheeted cover of the plane. It somehow adapts to how it coils. So anyway, this is what it does. I think it's pretty cool to see that you can actually drag it. You can see those folds propagating along the tail, and you can immediately see from this even that you could make the snake longer and longer. You could just keep attaching more and more segments at the end, and this thing would keep going.
The reason why I'm asking is that this was a snake. Snakes, and we are not experts on snakes, but
Me neither.
this is very similar to what is called in physics Roos model of a polymer. A polymer is actually your construction.
Yes.
The only difference
It's
is that
self-avoiding,
the wheels
right?
are
Yeah.
defined different than these pivotal points. And the questions how they bundle
Yes.
and coil
Yes,
in
yes.
2 dimensions
Yes.
is one of the crucial points, and
I see, yes.
Professor Cheplak is making a living out of the analysis of this issue. And the question is that they never can cross. The polymers never cross.
So this is
So there's
ignores this question totally. Well, okay, so we just figured out that we can drag the head whichever way we like, and the tail will follow. So what does it mean mathematically? I had this configuration space as a product of R2 and the torus, so I have those two projections. And what this statement means is simply that if I choose a point in M, and now I project tangent vectors using the projection P1, then the fiber of the distribution at M projects isomorphically onto the tangent space to R2 at the point below, which I identify with R2. So that I know, which, by the way, if you like to see it this way, you could say that D defines a connection in the fiber bundle P1, just an Ehresmann connection. There's no extra structure there. It's not a principal connection or anything, but just a connection. And in particular, that tells us that the rank of the distribution is 2, whatever the length of the snake is. Okay, so that's a very simple exercise that we have done here. We didn't really need to compute anything. So now we know the starting rank, so let's ask what the growth vector is. And we just put it into a computer, and we compute the growth vector at a generic configuration for the n-segment snake. Well, let's say we'll go up to n equal 10. By the way, before we do this, the growth vector is not very convenient because those numbers tend to get large. I define something that doesn't really have a name, so I'm going to call it an increment vector. That's not a standard name, I guess. So instead of taking those integers d1, d2, and so on, I take d1 and then the differences. Yeah, exactly. So I take the differential growth vector.
So the last increment is 0.
Exactly. The process stops and will never grow. Okay. Well, in this one you can see whether dr is equal to the dimension or not. In that one you have to add those numbers, so it's a bit harder. But on the other hand, it fits nicer on the page, and you can see some patterns, as you will see now. Okay, increment vectors for the snakes. So n is going to be the number of segments. Then I compute the increment vector, and finally this thing asks whether the distribution, whether iterated Lie brackets eventually span the entire tangent bundle. So whether this distribution is bracket generating. Okay, and we go on. I will just show you, well, what you see. So this is how it looks like. Up to this slight irregularity at the last position, what you see is 2, 1, 2, 1, 2, 1, 2, and so on. And you can start to believe that this is going to be this way all the time. Now, if you look at which positions you have such a 2, 1, 2, 1, 2, you see that it's sort of periodic with a period 3, and that's already a nice riddle. Why is it a period 3? Why does the increment vector for a snake of length, which is a multiple of 3, look this way, and not for snakes whose lengths are not a multiple of 3? And there are many questions here, and this is not at all obvious if you think about it. I have no idea. So this entire talk is about interpreting this result.
It looks like for arbitrary M.
No, unfortunately not. So the problem with this talk is that the main point is a conjecture that I have been unable to prove for more than a year now. But I have a lot of computational evidence, and well, I wish someone was able to prove it because I think it's quite interesting. So interpreting means not proving and not explaining why it is so, but relating it to something else that maybe has more substance to it, rather than just being a sequence of numbers. So the first invariant of distributions that has more substance than the growth vector is something that we call the symbol of the distribution at a point. So the symbol is also a pointwise invariant. I'm not going to define it because it's a little bit too technical, but I just want to tell you that at every point, this symbol is a graded nilpotent Lie algebra, so it's a Lie algebra. It has much more structure. It is canonically associated with the distribution, but the point is that the dimensions of the graded pieces of this graded Lie algebra give precisely the increment vector. So the entries in the increment vector are just the dimensions of graded pieces of some graded Lie algebra. So really they are just a shadow of some algebraic structure. And the bracket on this algebra is actually induced from the Lie bracket of vector fields. That's a very nice construction. However, as I said, it's a little bit too technical for this talk. But in fact, what is amazing about those snakes is that you don't really have to use the symbol. You can actually produce a Lie algebra in a much more direct way, and that will explain both the growth vector and the symbol. So we take a shortcut rather than defining what the symbol is. Okay, so now to the infinite serpent finally. So as you have seen, dragging the head along some curve in the plane will make the tail follow in some specified way, regardless of how long the tail is. So if you consider a snake, let's say with 100 segments, you could then look at the sub-snake with, say, 50 segments and with the same head, and every motion of the long snake compatible with the constraints will give a motion of the short snake, and vice versa. So
this language to each curve, which means the curve
yes,
that is followed
yes,
by
exactly,
the head,
exactly.
there is another curve
Exactly.
which is drawn by
Exactly.
and this connection between these two curves depends on n.
Yes, and it's actually a connection in the sense of differential geometry, because you lift those curves horizontally,
So
and they are compatible. So
when you map one curve into the other curve, then you need this parallel.
exactly, yes, yes, yes. So I have those configuration spaces. I label them n subscript n, and the distribution is d subscript n for the n segment snake. And I'm going to draw a diagram, but focus just on the bottom row for a moment. So here I have the 0 segment snake, which is just the head, the 1 segment snake, the 2 segment snake, the 3 segment snake, and so on. And I consider maps, projections between the configuration spaces that just forget the last segment. That's very natural. Forget the last segment of a 3-segment snake, you get a 2-segment snake. What is important is that this is compatible with the constraints. So if you have a 3-segment snake, you make it move according to the constraints, then you forget the last segment. Now you've got a 2-segment snake which is moving according to the constraints. And the other way around, if you take a 2-segment snake moving according to constraints, there is a unique way to make this additional 3rd segment move to still obtain a trajectory tangent to the distribution.
Unique, but depending upon the initial.
Yes. Yes. Yeah. Yes. Exactly. Yes. Yes.
And you mentioned that there are some similarities in the motion of this snake with length 3, 6, 9. This kind of period of 3.
If you look at the growth vector.
Yeah, but you don't see it somehow here.
Yeah. Not here. Not here. We'll get there. It will become clearer, I hope. So there is this picture. So what I do is I define M and D, which is going to be the configuration space of the infinite snake, as the projective limit of this data. So that's a standard construction in mathematics. What this means is the following. The configuration space is just, once again, a product, position of the head, and now an infinite torus, because we've got infinitely many segments. Okay? Now projections. There are projections from the infinite configuration space to each of the finite ones, and what they do is, well, they just truncate the sequence of angles parametrizing positions of all the segments, so they only give us the first n segments if we project onto the configuration space of the nth snake, n segment snake. And we've got a constraint distribution, so how is that one defined? Well, I take the distributions for each of those m's, I take the pre-images in the tangent bundle of M, and I intersect all those pre-images, which simply means that I am taking the, in some sense, the union of all the conditions that I impose on all the segments. So that's how you define the constraint distribution. And then you see that if you use one of these projections, then the fiber of a distribution in M will project isomorphically to a fiber of the distribution in an arbitrary finite snake. In particular, this means that this distribution is rank 2. So now this is very, very interesting because we've got this infinite dimensional configuration space and just a rank 2 distribution. So something very, very small. In some sense, we are going to see that this distribution is bracket generating. Now, since we are in an infinite dimensional situation, I would have to be much more precise, and I'm not going to be much more precise, so I'm saying in some sense. So in some sense, this distribution of rank 2 is enough to generate this entire infinite dimensional tangent bundle. Okay.
Can we think of this as a snake which has finite length, but the segments are shorter and shorter?
I always thought that it would be a very interesting way to view it, but I could never make it precise. I never really gave that much thought to it. That's a very, very interesting question, and actually it was pointed out to me when I was giving a talk about this at a conference in Bend Level last year, pointed out to me by Professor Roger Brockett, who's an expert in control theory, that there is some work that involves the dragging of a rope.
Yes, that's what I mean.
And I could never really later find this. I never really looked for it. I should perhaps. I don't know what do you get when you consider the dragging of a rope. So it's a different infinity though. It is a different infinity though. So this is yes.
So your snake becomes infinitely long.
Yes, exactly. It becomes infinitely long. But somehow you view it as a projective limit of finite snakes, which means that this long snake is filtered by finite length subsnakes, which share the same head. So, in particular, for example, the way you... Now, I don't want... Perhaps I will comment on this later. Basically, all the meaningful statements you could make about the infinite dimensional snake always have to be stated in the language of finite length snakes. So you can never utter a sentence that involves infinitely many segments. Of course there are. Of course there are. I mean, the point is that you have to choose some reasonable category of infinite dimensional manifolds, and I guess that in every reasonable category of these things, a projective limit should behave as it should. So if we want to be precise, I would say Sikorsky spaces. That this is one nice category.
I don't believe that this is relevant.
It shouldn't be. So since this is just a projective limit, this should work in with every reasonable notion of an infinite dimensional manifold. But of course, you have to be careful to define things precisely.
The other question which bothers me: if the snake is infinite, and if I drag it by this construction of these arrows, it will assume all possible configuration. Will that fill up densely, like ergodically, the plane?
Oh, I mean, can you use this snake to?
I mean, if it's infinite, there is enormous amount of
Yes.
And
So just by dragging, start with some straight snake.
Curves which fill up the, or the
Very nice question. I like it. Very nice question. Never thought of that. And I've never thought of that. It is a good thing to think of.
Because if it's infinite, can I?
Yes, I mean, so
all the points
so-
of the plane with the snake?
so you are able to. So in some sense, you are able to bring the snake arbitrarily close to any given configuration, but arbitrarily close has to be given a meaning. In an infinite dimensional thing, you have to. You need a topology on this space. And I stated in a projective limit topology, which is a very weak one. So
Well, since I don't know,
arbitrarily close means. So in other words, let's say that you want to, I mean, this is going to be almost a tautology. But let's say that you want the first 1 million segments to assume some configuration, you can always do it. Then if you want to improve, if you want the first 1 trillion segments to assume some configuration, you can do it. But
so
this is the best you can do.
So in a certain sense, arbitrarily close to a given point, there will be a configuration.
Yes,
So is
well,
it quasi-ergodic?
but this closeness is a very weak notion here, because closeness involves.
Position.
Yes, 2 points are close if they are the same for some finite. Sorry, not wrong.
The infinite tail of the
if they only differ by some finite amount of data.
But this is a combinatorics, and I don't believe
Yeah.
that these topological problems are relevant.
No, they... Okay, let me proceed.
Does not imply that
Because I want to...
question that they don't think
That's a very good question.
they should.
And I also, I mean, I would be very happy if I was actually hoping for that at this conference in Bend level, that I would meet someone who is a good analyst, who would be able to actually change my sort of formal constructions into things that are somewhat stronger, just by using some analysis on those spaces. But to me, it's all, let's say, algebraic and combinatorial. Whatever. Let's move to, in the direction of algebra. So we've got this configuration space of the infinite snake, and in particular, we take the projection onto the head. That's the zero segment snake. So once again, what we've got is that the fibers of the constraint distribution project isomorphically to the tangent spaces to the plane for all points. And this way, once again, this D gives a connection in the fiber bundle pi 0, if you have nothing against fiber bundles with infinite dimensional fibers, of course. What this means is that if I take any vector field on R2, so just a flow that tells me how the head would move, I can lift it to a horizontal vector field on the configuration space of the snake. Okay? So I have some configuration, I tell the head to move infinitesimally along some vector, I know how the entire configuration should move, so I can lift vector fields. So now, well, the simplest vector fields on R2 are just the coordinate vector fields. And I lift them to things that I call X and Y. So capital X and Y are some vector fields on this infinite dimensional configuration space, and they span the distribution D. So I call them the generators of D. So in order to understand this distribution, what I can do is to start taking Lie brackets of those two vector fields. So I'm going to do it.
These vector fields have an index n, depending on are they universal?
No, there's no n anymore because we've passed to the infinite limit. This is exactly why I do it. Because things get more regular in the infinite limit. Yes, things get more regular there. So this M is now this infinite dimensional space. Because I could do it for every n, and then I see that things are compatible, so why not work with the limit? So,
in what sense this limit exists?
So once again, this is the answer that was already asked by Mikołaj. So you could interpret it using various notions of infinite dimensional manifolds.
In physical terms.
As a limit.
Yeah, so in physical terms, the way you do it, the most important thing on such an infinite dimensional manifold is the question, what are smooth functions? So smooth functions on M are pullbacks of smooth functions from all the finite dimensional configuration spaces. So to give a smooth function on this infinite dimensional configuration space, you can write any smooth function of a finite number of segments. But you cannot write anything that involves infinitely many. So you know then what is the...
Snake is nothing but the limit of finite.
Yes, exactly. So it is just a bookkeeping device. There is no... there is no value added in this construction. It's just a bookkeeping device. So we've got those vector fields, whatever it means. I don't want to go into technicalities now.
And you don't have an explicit form of this?
Actually, I do. I do. This is not difficult. This is not difficult, although it's not very enlightening, at least to me. But I do, and I actually compute things. So I compute with a computer how the Lie brackets look like.
Point. It's very important because to each motion in the x direction, you have some motion in the...
Yes, absolutely. I have formulas.
Yeah, but that's trivial this arrow.
Yeah, exactly, yes.
Yeah, but this is the limit. No, this is...
Well,
In the limit, I mean, in the limit.
Yes,
This arrow is
exactly.
closer and closer, but the physics is...
Let's get to that later.
The rigidity of this.
We can discuss it later. I mean, there are many interesting things I can say about it, but I don't want to do it now because I want to get to my point. So, start with those two vector fields, x and y, on the configuration space. They sit in the distribution and they span the distribution. Now I'm going to take commutators. Okay, so in degree 1, that means no commutators taken, I have x and y. Now I have the commutator of x and y, there's nothing more I can do with that. Then Well, all I can do is commute it with x or y, nothing further. Now, interesting things happen in degree 4, because I just get one independent vector field that can be written in terms of those 4 commutators, and there are some relations. So I could also write such a thing, and a priori this could be independent from that, but it is not. Those two are actually equal. That's what you get. Now, you could also write these by Jacobi identity. This has to be equal to that, but actually both are equal to 0 in this example. So you see the approach. Well, you could generate a free Lie algebra from x and y just using Jacobi identity.
It's minus or equals?
The first one is minus. The second is equals. The reason I chose this notation is that this equality is not a relation, because this is actually Jacobi identity. So it has to be imposed. Whereas those two could be different. So you see that once you take a quadruple, no, that's a triple commutator, you start seeing that, well, this Lie algebra is not a free Lie algebra on x and y, but there are some relations. So you want to understand those relations, and this way identify what is this Lie algebra that you generate from x and y. Okay, so after looking at it for a while, I realized what it is, and I'm just going to tell you the answer. It's a loop algebra. So I'm just going to do a very, very quick introduction to this notion just for this particular case. So the ingredients are the following. Start with the Lie algebra, I will call it G, that's just SL2R, trace-free 2x2 real matrices. Okay. Now, consider the Cartan involution. So this is something that takes a matrix to negative transpose of that matrix. You should think of it in the following way. The subspace of SL2 fixed by theta is SO2, okay? And this theta leads to a symmetric decomposition of G. Now, third ingredient is the Laurent series ring. So Laurent series in some variable t with real coefficients. How does it look like? Well, those are just formal power series where you allow only finitely many negative powers, right? And infinitely many. Yes. And this is formal, so no question about convergence. That's just pure algebra. Okay, so we've got those 3 ingredients. Now, the loop algebra of G is just a tensor product of these. So you could think of these as formal power series, Laurent power series, with values in the Lie algebra G. In other words, elements of Lie algebra G that are parametrized by T, but, well, really by some formal Laurent series. Okay, and there is, if you allow your imagination to really think of these as functions with values in G, with some variable T, then the bracket is just pointwise. The Lie bracket is just pointwise, which would mean that if you want to take a Lie...
Pointwise with respect to T?
Yes. Which just means that if you want to take a Lie bracket algebraically, you take a Lie bracket in G and you multiply the power series in here. Okay? So that's what you call a loop algebra. That's a Lie algebra still. That's a Lie algebra. And now what we needed is a so-called twisted loop algebra. So we twist by the involution theta. What it means that we only take such elements in the loop algebra that if we evaluate them at negative t, that corresponds to applying the involution. So there's some kind of a symmetry condition. That reflecting t is the same as applying the involution theta in the Lie algebra. Well, so it is.
And why it's called twisted loop?
It would take me a few minutes, so I'm going to answer this later. Sorry, I'm sorry. It's a very good question, and it's a very nice story. Although the loop here is rather irrelevant, because if I do it over the reals this way, this has nothing to do with loops. If you were to complexify this could be interpreted in terms of loops. So these are not really loops. So there is no nice geometric interpretation here. I mean, there is, but not as attractive. Okay, last thing, negative subalgebras. So I could take a subalgebra in the loop algebra where I only got negative powers of t. You can ask me why negative and not positive. Well, this is just a convention. For some reason, we like negative. So I mean, here it differs really. So, okay, but we could do it the other way around. So we only take negative powers of t tensored with elements of G, and this is then naturally graded. So there's a graded subalgebra, where the ith graded piece is just G tensored with t to the power I. And of course, if you now take brackets of such things, then those powers of t's are multiplied, so the exponents add up. So this way you see that this really gives you a graded Lie algebra. And you can do the same in the twisted case. So for the twisted one, those graded pieces are just the intersection of the graded pieces of the full loop algebra with this twisted subalgebra. It's interesting to see how they look like. So the ith graded piece of the negative twisted loop algebra is, well, here the exponent is going to be I, and in G you take the subspace that is fixed by either theta or negative theta, depending on whether I is even or odd. That's a lot to absorb in just a minute, but that's the construction you do. So, one last thing, and I can at last state my main conjecture. So this involution, the Cartan involution on the Lie algebra SL2 gives a Cartan decomposition. It decomposes G into the maximal compact subalgebra and an invariant complement. In this case, this maximal compact subalgebra, which is the subspace fixed by theta, is just SO2, and the complement is just R2, on which SO2 acts in the obvious way. So this way, you see what are the graded pieces of our twisted loop algebra. There should be a frac G here that I forgot. For even i's, you just get R, the trivial SO2 representation. For odd ones, you get R2, so the standard representation. Well, now if you think about it, so you get negative integers, even, odd, even, odd, even, odd. You look at the dimensions of those spaces, you get 1, 2, 1, 2, 1, 2. That should ring a bell. So here's the conjecture. So, I have to start with the following. If I look at the negative 1 graded piece of the loop algebra, twisted, that's just R2. I'm going to map it into sections of the distribution D by simply sending some orthonormal basis of R2 to the pair X and Y. Orthonormal makes sense because this is naturally acted upon by SO2, so I know what orthonormal means. Now, an important fact is that this entire negative subalgebra is generated by its degree -1 part. So this map, in principle, should give me a map from the full negative part of the twisted loop algebra into vector fields on the configuration space. It does so if the relations are satisfied. And I claim, that's a conjecture, that it does extend. I mean, uniquely is obvious, there is just one way to extend it. The non-trivial part is that it does extend. So in other words, if I look at this algebra generated by X and Y, I'm saying it is precisely this negative part of the twisted loop algebra of SL2. That's what I'm saying. It's precisely that. So I identify this Lie algebra, and moreover, there are some neat technical points. So first of all, if I take this map, so it maps into vector fields, and now I evaluate at some fixed point, then I get an injection from this algebra to the tangent space. Well, the tangent space is infinite dimensional, so that's not surprising. And then if I project it to an arbitrary finite snake, I get a surjection on the configuration space. So in some sense, I've obtained a frame, in some weak sense. And I'll comment on that in a moment. So that's the conjecture. Now, what are the consequences of it? So first of all, it tells us exactly that the increment vector of our distribution is 2, 1, 2, 1, 2, 1. So that's the thing I wanted to answer. So I gave an interpretation to this 2, 1, 2, 1, 2, 1, and so on. But that is now, well, now it is not really the most essential point. We've gone much further than that. So whatever the symbol is, actually I also identify the symbol. The symbol is isomorphic exactly to this negative graded Lie algebra. So this answers the question about the symbol, but we don't talk about that here. Now the more interesting thing is that at each point of our configuration space, we now got a kind of a frame with values in this Lie algebra. Why a kind of a frame? Well, because, as I said, it is an injection, and its image is dense in the projective limit topology. So if you've got some injection from some vector space whose image is dense in your favorite topology, that is sort of a frame. This topology is very weak, but still we can, it should tell us something. Now, if you've got a frame with values in a Lie algebra, then perhaps your manifold is actually a Lie group in some sense. And in a well-defined sense, it turns out that this configuration space with its distribution is formally, I'm not saying what that means, equivalent to a Lie group integrating this infinite dimensional Lie algebra, where the distribution is a left invariant distribution defined by the degree -1 subspace of the Lie algebra. So formally, my configuration space is a Lie group. And formally, my distribution is a left invariant distribution on a Lie group. That is nice, but it's formal. And I can later tell you what this formal means if you ask me. And better yet, in fact, there is a bigger symmetry group, formally. So there is a formal action of the full twisted loop algebra as symmetries of the distribution. So that looks quite interesting. If you think about finite length snakes, the best they can have is sort of Euclidean symmetry and I guess homothethy. So it's at most 4-dimensional for any finite snake, except for the one-segment snake, which has projective symmetry. But suddenly, once you get to infinite length, you get this infinite dimensional symmetry, only that it's really formal, so it's not true, and who knows what can it really give you. It's not an honest symmetry, but it is there, and in some sense it should be meaningful.
It is different.
Yes, exactly. It does not descend to any finite snake, exactly. Yes, this is the problem with it, exactly. Yeah. That's exactly the problem. That it does not, it cannot be interpreted on the level of finite length snakes. So that's what makes it so elusive. So anyway, that's the last slide. In conclusion, the status of this conjecture is the following. I have massive computational evidence, which means that I computed those things. So basically, how do you do it? You check the relations. There are finitely many relations in every degree. Basically, for every 2 degrees, you've got 3 relations. I checked up to degree 20 in the number of commutators and up to a 20-segment snake. And this takes maybe, I don't know, 10 minutes on a computer, so I could check for much more, but I believe it is true, so I am quite convinced, but unfortunately, I have no proof. Now, I also have some well-supported explicit formulas for all the vector fields in the image of psi. So not only x and y, but also all commutators of x and y. But these are terrible combinatorial formulas. It's just terrible combinatorics. I can do nothing with that. It's just way too complicated. I can only check, once again with a computer, that it agrees for snakes up to some length and for degrees up to something. Now, my questions that I think are most important to me are the following. So first, if you take this group, let's say, SL2 and the Cartan involution, then this actually defines the hyperbolic plane as a symmetric space, as a Lie group with an involution, simple Lie group that gives you a symmetric space where this involution, its fixed subgroup is the maximal compact subgroup. So what is the place of this hyperbolic plane in our story? I know how to find a place for the hyperbolic plane for a single segment. I learned this from our friend Gilbert, but I don't know how to really answer those bigger questions with that. But it has to be there. I feel this. So that's one question. And the second question is, what good are our formal symmetries? So what is their significance? I've never seen anything like that, so I don't know how to work with that. But they are there, and they should give us something. And finally, returning to the original program, the question is, does it really teach us something about this initial problem of whether we can deduce a growth vector from the combinatorics? So I would say that, I mean, it tells us that this idea of just guessing the growth vector is rather hopeless, because I would never guess that this growth vector is just going to be 2, 1, 2, 1, 2, 1, and so on. But maybe some conclusions can be drawn. So I end with this conclusion, and I will happily answer any questions. Thank you.
Those
Yes.
different lengths.
Exactly.
And I believe that Professor Wojnicki's proposal to treat this infinite snake as finite and go to the limit with maybe because then they will become some infinitesimal in symmetries.
But then the
I
question,
believe this is a
that
crucial
if you
point.
Very
go
possible.
to the limit, then you have a problem that the wheels will collide.
Yes, and you are very right. And if you look at the behavior of the snake, it has a tendency to develop those folds, as you can see. So somehow you might think that in some continuum limit, this curve is almost always going to be some terribly non-smooth, irregular thing.
With several dots.
Yes,
Not
but
necessarily. The Peano curve is smooth, but it's full of those things.
yeah, but those are very cusp-like. So they're not corners; they are
Yeah, they
literally
are
cusps.
because you have a finite length.
Maybe, yes. So I don't know. Maybe it works. Yes, exactly.
Do you have a formula for capital X in terms of dx and dy? Or this is not needed?
I mean, I do have it in various guises, and I'm thinking of where should I find the easiest one. So let me see if I have another version of this presentation, and maybe this is a good idea. Maybe it's there, and if not, I can show it to you, but in a moment. So I don't have a version that's readily readable. Let me just quickly tell you how you might want to write it. Or do I have it here? The point is that basically the coefficients of such vector fields are functions on the torus, so you want to do a Fourier transform. Or in other words, they are given by some trigonometric polynomials, so you rather transform them to some...
It's rather complicated.
It is not. It is remarkable if you do it right, but let me just see if I can find it here. So that's a different version of this talk, and maybe I have...
From a physical point of view, that's
Maybe I have it.
important to know an explicit formula.
Yes, absolutely, yes. Do I have? No, I don't have those explicit formulas, but let me just tell you in words. So I will tell you in words. So, first of all, what really matters is only the torus. The R2 is not very important. So you could take those vector fields and project them onto the torus. They project nicely. So really it's important just to understand the vector fields on the torus. And then you want to do a Fourier transform and just look at the... So then you get some functions on some lattice, right? And the remarkable thing is that...
Fourier series rather than transform.
So, yes and no, actually. So let me tell you what you get. So if you take a finite snake, so you've got a finite dimensional torus, and you take a correct parametrization of the angles, I'm not saying what it is, but there is, some are better than others, obviously, then actually this entire Fourier transform is supported only on, so now you're on a lattice. So a point of your lattice is just an n-tuple of integers. So it is supported only on n-tuples where each entry is either +1 or -1 or 0. And even better, now if you start taking commutators, you never get out of this support. So that's quite remarkable. But this is exactly like if you look at Lie algebras of vector fields on the circle, and also Fourier transform those vector fields, then SL2 is the biggest finite dimensional algebra of vector fields on a circle, and it exactly is supported only on -1, 0, and 1 as the Fourier, how should I call it, mode numbers, right? And it's very similar. So on this torus, once again, we've got, that's interesting in its own right. We've got some Lie algebra of vector fields on a torus. If the torus is finite dimensional, then it's a finite dimensional Lie algebra. And if we Fourier transform those vector fields, then the resulting transforms are only supported on this time, let's say, mode, I don't know, strings, right, where all the entries are -1, 0, or 1. That's quite remarkable, because this is very special. You would imagine that if you take some random things and you take commutators, this just gets all over the place. So I have formulas for x and y in terms of this, and so I can look them up in a paper later. But in fact, I also guessed formulas for all the possible commutators, and there I get into this horrible combinatorics, and I can check that, yes, they actually do work for very high degrees and pretty long snakes. I have no idea why, and I don't know how to check the relations. So it's mysterious.
No, thank you.
Thank you.